For centuries, the story of our planet was a timeline without numbers. We knew some civilizations came before others, that deeper layers of Earth were older, but the vast expanse of prehistory was a mystery. That all changed in the 20th century with the invention of chronometric dating, a suite of scientific tools that act like atomic clocks, allowing us to assign concrete, numerical dates to the past. Today, we're unlocking that toolkit to see how science measures deep time. Perhaps the most famous of these tools is radiocarbon dating. Its discovery didn't start in an archaeology lab, but in the world of physics. In the 1940s, chemist Willard Libby had a brilliant idea. He knew that cosmic rays constantly bombard our upper atmosphere, creating a rare radioactive version of carbon called carbon-14. Libby hypothesized that this carbon-14 would combine with oxygen to form radioactive carbon dioxide, which is then absorbed by plants during photosynthesis. Animals eat those plants, and we eat those plants and animals. The result is that while an organism is alive, it's constantly exchanging carbon with the environment, maintaining the same ratio of carbon-14 to stable carbon-12 as the atmosphere itself. But the moment that organism dies, the exchange stops. It no longer takes in new carbon. The carbon-14 it has accumulated is no longer replenished, and, being radioactive, it begins to decay at a perfectly predictable rate. The half-life of carbon-14 is about 730 years. This means that if you have a sample of wood, after 730 years, half of its original carbon-14 will be gone, having decayed back into nitrogen. After another 730 years, only a quarter will remain, and so on. By measuring the ratio of carbon-14 to carbon-12 left in an ancient piece of wood, bone, or fabric, and comparing it to the known atmospheric ratio, scientists can calculate how long ago that organism died. This revolutionary idea earned Willard Libby the Nobel Prize in Chemistry in 1960. However, there was a catch. Libby initially assumed the amount of carbon-14 in the atmosphere was always constant. We now know it fluctuates due to changes in solar activity and the Earth's magnetic field. So how do we correct the clock? The answer was found in trees. Using dendrochronology, the science of tree ring dating, researchers analyzed individual rings from long-lived trees like the bristlecone pine. Since each ring represents a specific year, they could measure the carbon-14 in each ring and create a calibration curve. This curve allows us to convert a raw radiocarbon age into a precise calendar date. The impact of this calibrated technique was staggering. It helped verify the age of the Dead Sea Scrolls, dating their linen wrappings to a period between the 3rd century BCE and the 1st century CE. It told us that Otzi the Iceman, the stunningly preserved man found in the Alps, lived about 300 years ago. It was even used on the famous Shroud of Turin, with results placing its origin in the Middle Ages, between 1260 and 1390 CE. But carbon-14 has a limit. Because of its relatively short half-life, it's only reliable for dating things up to about 50,000 years old. To peer deeper into geological time and the story of early human evolution, we need clocks with a much longer tick. This is where methods like potassium-argon dating come in. This technique is a cornerstone of paleoanthropology, capable of dating volcanic rocks millions or even billions of years old. The science is based on the decay of radioactive potassium-40 into the inert gas argon-40. Potassium-40 has an incredibly long half-life of 1.25 billion years. The clock starts when molten rock cools and solidifies. As minerals crystallize, they trap potassium-40 inside them, but any argon gas present is driven off by the intense heat. So the rock starts with 0 argon. Over immense timescales, the trapped potassium-40 slowly decays into argon-40, which remains trapped within the mineral's crystal structure. By measuring the ratio of potassium-40 to the accumulated argon-40, scientists can calculate how long it's been since the rock cooled. This method famously rewrote the story of human evolution. In the 1960s, Louis and Mary Leakey found fossils of early hominins at Olduvai Gorge in Tanzania. The fossils were sandwiched between layers of volcanic ash. By using potassium-argon dating on these ash layers, scientists determined that these early humans lived around 1.75 million years ago. In a single stroke, this discovery nearly doubled the accepted timeline for human evolution and cemented Africa's role as the cradle of humankind. For dating the truly ancient, like the Earth itself, we turn to one of the most robust methods available: uranium-lead dating. This method has a unique advantage. It uses two separate decay chains as a built-in cross-check. The isotope uranium-238 decays to lead-206 with a half-life of about 4.5 billion years, while uranium-235 decays to lead-207 with a half-life of about 700 million years. The ideal mineral for this method is zircon. When zircon crystals form in cooling magma, they readily accept uranium atoms into their structure, but strongly reject lead. This means the clock starts at a pristine zero. By measuring the ratio of both uranium isotopes to their respective lead daughter products, scientists can calculate two separate ages. If the two ages match, they are called concordant, giving a very high degree of confidence in the date. So how do you date the Earth, a planet whose oldest rocks are constantly being recycled? You look to space. In 1956, geochemist Claire Cameron Patterson analyzed lead isotopes in meteorites, which are pristine leftovers from the formation of our solar system. Using the uranium-lead system, he calculated an age for the Earth of 4.55 billion years, a number that has stood the test of time and remains the accepted age today. But what about things that aren't organic and aren't volcanic rock, like a piece of ancient pottery? For this, scientists use a fascinating category of techniques called trapped charge dating. Minerals like quartz and feldspar, found in clay and soil, act like tiny rechargeable batteries. Over time, they absorb energy from natural background radiation in the soil, which knocks electrons loose. Some of these electrons get stuck in defects within the mineral's crystal structure. The number of trapped electrons builds up over time. The clock is reset by an intense event. For thermoluminescence, or TL dating, that event is heat. When a potter fires a clay pot in a kiln, the intense heat releases all the trapped electrons, setting the clock to zero. After the pot is used, discarded, and buried, it once again starts accumulating trapped electrons. To find its age, an archaeologist carefully heats a sample in the lab. This releases the stored energy as a faint glow of light. The intensity of that light reveals the total radiation dose the pot has absorbed since it was fired. By dividing that total dose by the annual radiation dose of the soil it was buried in, you get its age. A similar method, optically stimulated luminescence, or OSL, is used to find out when a grain of sand was last exposed to sunlight. For these grains, light is what resets the clock. Once a grain is buried and shielded from the sun, it starts trapping electrons. In the lab, scientists expose the grain to a specific wavelength of light, which causes it to release its stored energy as a signal. This has become a crucial tool for dating ancient sand dunes, or the layers of sediment at an archaeological site. The field is constantly advancing. One of the biggest game changers has been accelerator mass spectrometry, or AMS. Instead of waiting for carbon-14 atoms to decay, which is slow, AMS uses a particle accelerator to separate and count the carbon-14 atoms directly. This means the sample size needed is about 1,000 times smaller. Scientists can now date a single seed, a tiny fiber from a textile, or even residue on a tool without destroying a precious artifact. These powerful techniques force us to confront important ethical questions, especially when analyzing human remains. Curators and bioarchaeologists must weigh the scientific knowledge gained against the need for cultural sensitivity. and respect for the deceased and their descendant communities. Destructive analysis is now typically reserved for answering very specific research questions that justify the process. From the faint radioactive whisper of a single atom to the trapped light in a grain of sand, chronometric dating has given us an absolute timeline for history. It has revealed the multi-million-year journey of human evolution, the true age of our 4.5 billion-year-old planet, and the intricate tapestry of civilizations that rose and fell across millennia. These atomic clocks continue to unlock the secrets of our deep past, reminding us that history is not lost but merely waiting to be measured.